Hello everyone. Uh, Mr. Fipika, I see your hand is raised. I hope I pronounced your surname correctly. If you need to ask me anything, just type it or ask. Okay, good afternoon, ladies and gentlemen. Today will be our final Yaba physics session for me. I think the other tutors still have some left, but today there is just 7 quick questions, and they all have to deal with optics, ray diagrams, and so. Okay, they are quick, easy, and I hope that you understand. Okay, now what I need from you guys is whenever you don't understand anything, just ask me, and I'll try to explain it if I can. Now, I do not know everything, but I do this every year, so I know more or less the questions that I might get and encounter. Okay, so I'm not going to waste any more time. I don't think there will be a lot, so you guys, thank you for joining. I'm not going to keep you, hopefully, not more than a half an hour. Shouldn't be more than half an hour. Okay, so let's go immediately into the questions, unless there are any. I see a raised hand. Uh, Mr. Sapika, your hand is still raised. I don't know if you have a question or is that very good. Okay, just by show of a thumbs up, do you guys, can you see the screen I'm sharing? Can you see the screen I'm sharing? Can you guys hear me? Okay. Okay, can you hear me now? We have not started yet. Can you guys hear me now? Okay, thank you. Okay, now I was just saying, sorry, there are two mics here. One is for the camera and one is for the actual Razer mic in front of me. Now, this should be quick. We are finishing up, well, I am finishing my last for this year. The other two, I think Arnold and Jeb still have tutorials left this week, but it will be on optics. Okay, just raise your hand if you can see what I'm sharing at the moment. I won't keep you here longer than half an hour, well, 25 minutes at the most. This should be quick. It is just has to deal with ray optics. Okay, so far you have almost done with optics, so you should be able to do this real quick. Okay, should able to spot a real or virtual image immediately. Okay, now let's go to question number 31. Don't, the numbering is just for us. Okay, just look at the question. The numbering is for us so that we divide the questions equally amongst the tutors. Okay, so let's say they tell us the image of an object beneath the surface. Okay, so we have, let's say we have here a dam. Okay, and there is a fish. Okay, There's a fish. Okay, smiling fish. This is how I used to draw a fish. Okay, so we have a fish. Okay, it is underwater. Okay, there is the surface of the water. There's the fish. Now, this medium has a refractive index of bigger than 1. Okay, so the medium has a refractive index bigger than 1, and it is seen by a person looking down on the surface. Okay, so there is a person here on the bank. Let's say he's fishing or whatever it is he's doing, and he's seeing this, is looking down, okay, at this fish. This image that this person sees, formed by the light rays, okay, leaving that flat reflective surface is. So what does this person see that's standing here? Okay, does he see a real fish? Does he see a virtual fish? Does he see this fish close to him, or does he see it farther away from him? Now let's think about this. Okay, let's think about this. Now I'm going to not look at there at my drawings. Okay, so light travels from this object, this fish. Now it travels from the fish to the viewer, right? In normal cases, the light will travel straight from the fish to the viewer. Okay. Normally, this is what would happen. Okay. The light will travel straight from the fish to the viewer's eyes. Okay. You guys agree? That's what would happen in a normal situation. If both of these had the exact same refractive index. Okay. That's what would happen normally. Okay. Now, this light, they tell us, is refracted because this one has a refractive index bigger than 1, while air, we know, has a refractive index of 1 itself. Okay, air has a refractive index of approximately 1. Let's not say 1, it's 1,000. So air has a refractive index of, I can't just make this thing right. Okay, let's see. Yes, that's better. Not beautiful, but better. Okay, so air has a refractive index of approximately 1. Now I'm going to keep the chat open. Uh, Miss Shabalala, can you hear me now? Miss Shabalala, can you hear me? I see you typed there that you can't seem to hear anything. Can you just type whether you can hear me? Okay, it seems that you can't hear me. Well, everyone else can hear me, so this must be at your end, or okay. So now we have this fish. Okay. Now, due to light being refracted, okay, let's say this is the normal to the surface of this pond. That's the normal. Now, normally, what would happen normally? Now I'm going to draw this in different lines. Okay, let's go back. Normally, what would happen? And I did show this earlier on. This is what would happen normally. The light bouncing off the object, which in this case is the fish, would go straight to the eyes of that uh, person there. Okay? But this is not a normal situation because light is traveling in mediums with two different refractive indexes. Now, when light crosses the flat surface to enter the air, okay, now when light comes from the water, let's say in this case it's water, we're just making an example. When it comes from the air, it breaks away from that. The angle here is much bigger than the angle here. Okay, it diffracts. Okay, so the light diffracts. Okay, it breaks away from the normal. Okay, this is what happens to the light. We have the fish here. Light goes, let's say that's the normal. Light from the fish goes their way and then it breaks away from the normal. This angle is much bigger than this angle. Okay, the light breaks away from the normal. Okay, let me clean that. Okay, so now you understand what is happening. Okay, the light is breaking away. Let me just redraw this. Then we have the fish. So, and then of course we have the person standing right here. Looking at the fish. Okay, so, and of course this is approximately 1, and this they tell us is bigger than 1. I see a lot of people just join. This is the situation. We are looking at an object. In this case, I drew a fish where the refractive index is higher than the refractive index of the air. So light is going off from this fish. So light is going off from the fish in a normal situation. Of course, like I said, normally it would go straight from his eyes or straight from the fish right. Let me redraw this. Straight from the fish to the person's eye. That doesn't happen in a normal situation. Okay, this is the normal situation where n, this is, let's call this n2 and this n1. Okay, where n1 is equal to n2. This is in a normal situation. The light would just go straight because light moves in a straight line. Okay, so the light is moving in a straight line, but this is not a normal situation. So what will happen to this light? It's going to go and then it's going to refract. Okay, by show of hands, can everyone hear me? Just show, any one of you, can you show a thumbs up that you can actually hear me? Just anyone. Okay, can you hear me now? Okay, okay. Can everyone hear me now? Okay, cool. Now, normally, like I said, you would just look at the object and, okay, normally you would just look at the object and the light from the object would travel in a straight line. But they tell us that the refractive index of this substance is higher than that one. That means the light will bend away. If this was the normal, remember there's always a normal where they meet, the light would bend away from the normal. Okay? The light would bend away from the normal. Now, this is what what normally. Now, since that is what would happen normally, light would just travel in a straight line. This is what will happen in a normal situation. Okay? What happens when n is bigger than that? This is what's going to happen. And we have that. And downwards. Okay. This is what's going to happen with this difference in refractive index. Okay, this is what happens with the difference in the refractive index. So what you're going to see now, normally you would see the fish there. Let me just, normally you would see the fish here, but now you see the fish here. Okay, if n is bigger than 1, this is what happens. Okay, the light is bent towards, away from the normal, so the fish would appear to be much closer than it actually is. Okay, the fish would appear to be much closer than it actually is. So you are not actually seeing the actual fish, you are seeing a virtual image of the fish. Okay. Okay, let me just see what is happening with the mic. Can you guys hear me now? I canceled the noise suppression. It seems the noise suppression was giving the problem there. Okay. Do you guys understand what is happening here? Okay. Let's look at this. Normally, this is what you would see. The light rays would travel in a straight line from the fish. Remember, this is the actual fish. This is real. This is real here. This is the real fish. Okay? That's the real fish. Uh, my thing, the noise suppression was down and it counted. It's supposed to work like this, that it cancels any noise around, any background noise. It will eliminate, but it eliminates something. I'm the only one in this room. It's quiet. It counts my voice as noise and then suppresses it. Okay, so this is the real fish here. Okay, this is the real fish. This is the real fish. Okay, now normally this is what would happen. The light would travel straight from this fish to the eyes of the observer. Okay, if n here was 1 and n here, or the n was the same. Now, in this case though, n here is different. Okay, this is bigger than 1, which means when light travels, it will bend towards the normal. Or what happens when light moves from a lower refractive index to a higher refractive index? It bends towards the normal, right? It bends towards the normal, and this is what's happening. Okay, normally the fish would be here. In an ideal situation, the fish would be here because you would see it straight. There would be no difference in the refractive index in the air or in the water. But since there is a difference in the refractive index, the light ray is bent. In this case, this one is n is equal to 1. This one is n is equal bigger than 1. So it is bent towards the normal, meaning you're going to see the fish here. Okay, you are going to see the fish much closer than it actually is because of the light rays being bent. And not only that, you are not actually seeing the real fish. This is the real fish here. This is the real fish at the back. That one is real. That's the actual fish. This one is a virtual image. Due to the bending of the light rays, you think the fish is here. The fish is not actually there. It's here. But due to the bending of the light rays, you see a virtual fish, and you see that this fish is much closer to you. Okay, so you see a virtual fish, and it is much closer to you. Now, this is what happens when you look at something, say, in the water. Okay, if you were to look at anything in the water, a fish, if you were to look at a fish in the water, let's say you have a fish tank, and you are looking at you can ask a question. I think it's everywhere. Go ahead.
Hello, sir.
Yes.
So how how much is the distance from the original fish to the virtual fish?
You can calculate that if you have the actual numbers, but you are going to have to calculate the refractive indexes here, and then using trigonometry, calculate this length, and then work out the difference between those two. Okay, you're going to calculate, but we never actually asked that. But do you understand that the virtual fish
Yes.
and the real fish, the virtual fish seems much nearer than it actually is.
Okay, thank you, sir.
Okay, but you can calculate it using simple trigonometry. Okay,
I see.
okay. Now, so the question was, if you are looking at something, in this case, I made the example of fish. Okay, the only difference is that needs to happen is that one medium where the object is needs to have a higher refractive index. So in n needs to be higher than the n that you are in. In this case, the refractive index of air is lower than the refractive index of water. So I use that example. So if you are ever looking at a fish, let's say you're standing at the edge of a lake or at the beach or in very a pool and there's somehow a fish or someone in the pool. Okay, you see someone underwater standing at the edge of the pool. The person you are seeing underwater is much closer to you. It's not the actual person. You don't see the actual person. You see what the light rays are projecting. You see, okay? You are seeing a virtual image, and it is much closer than you think. So the actual person, if you want to, let's say you want to throw this person with a brick. That is a harsh example, but nonetheless, it's the easiest way you'll understand this. Let's say there's someone in the pool you don't like. You have a brick. You want to throw this brick at this person. What you should do is aim a little distance behind that person, because the person you are seeing is a virtual image, and that person is not actually where you see they are. They are a bit behind. You are seeing a virtual image that is closer to you. Okay, does everyone understand that? Aviwa, you can go ahead if you have another question.
Yes, sir. So if we're not seeing the original image or the object, what makes the virtual image to appear?
It's the
You
bending of the light rays. You are still seeing, technically, you are still seeing the actual person, but you are not seeing where this person is in real time. Okay, you are seeing, you are seeing this. Let's say this is this person that you don't like. Here you are at the edge of the pool with your brick. Okay, here's this person. Okay, you are not actually seeing the person. This is where the person is in reality. Okay, but you
yeah.
are seeing the person here, slightly in front of where you are. This is where you see the person because of the bending of the light rays. The light rays are bent, and it's coming from this person. But in actual fact, the person is actually here in reality. If light rays was to, usually which tends to move in a straight line, the person is actually here. This is actually where the real person is. But due to the bending of light rays, the person appears to be here. The person is not actually here. They appear to be there. Okay? But now it's slight. It is so slight. It is about millimeters or nanometers off. Okay? It is very slight. Does that make sense? Everyone?
Okay. So
Okay.
it's not a huge difference.
It's not a maximum like a huge difference. Okay?
Okay.
It depends on what this is anyway. If this is water, the difference between the refractive index of air is 1 and water is 1.3. So it's about zero point 0.3 something something. Anyways, you
Okay.
could
Thank you, sir.
calculate it actually, but this person is slightly. You still hit them with the brick, don't worry. But if you want to hit a certain spot, you'll be off by millimeters. Okay? So here's the amazing thing though. You guys have seen, I love watching National Geographic channels where especially, have you ever seen a fish eagle catch a fish? This thing is so amazing. It has this built-in calculator where you remember it, just like us, it sees where the fish is virtually. It does not see the actual fish. It sees where the water tells the fish is, but that's not where the fish actually is. Okay? This thing can calculate for that. It compensates for that. That's why it can swoop down and catch the actual fish, not the virtual image that is shown by the the light rays coming to its eyes. Okay, that's the amazing thing about fish eagles and all of the stuff that actually catch prey in water, which comes from the air to the water. Okay, they see a different image, but they have a built-in calculator that compensates for that refractive index of water. Okay, so let's move on to a different question. Now, note if you are looking at anything with a refractive index bigger than where you are, okay, if you're looking at anything bigger with a bigger refractive index, whatever you see will be closer to you and it will not be the actual thing. Okay? Which makes sense. If it's closer to you, it's not actually the thing that you are seeing because the real thing is at a set distance. It is virtual and it's closer to the viewer than the actual object. And that is the correct question. Now let's look at question number 2. Now we can calculate actual depth of a pool and what you see as the depth. Okay. I think this will go to a viewer's question earlier on. The slight differences, and I don't know who asked. Was it a viewer still who asked that difference in the distance? Okay. Let's see. Let's say the actual depth of a shallow pool is about 1 meter. Okay, so we have the actual depth is 1 meter. But the depth that you see, you don't actually see 1 meter. The apparent depth, when you look straight down the pool from the above, okay, how deep do you think it is? Let's say you are standing here. This is the pool. Here's the pool. This is the pool. You are standing here. Okay. No brick this time. You're about to dive. Now, in actuality, this pool is 1 meter deep. Okay. This pool is 1 meter deep. Okay. There's the water. Nice cool water. Summer's coming. The pool is actually 1 meter deep. They took a stick. They measured the pool is 1 meter. Now, they say that the apparent depth, what is the depth that you see? When you look in this pool, what depth do you see? Okay, how deep do you think the pool is? Let's look at it this way. Let's see. Now, there is a formula. It says that the refractive index is equal to the real distance, and you can write this formula down or you can remember it. Okay, I'm not going to show you how you derive this formula, but just know this. The real depth divided by the apparent depth will give you the refractive index. Okay, now this is the formula. It says that the refractive index, which in this case is 1,33, is equal to the real depth, this measured depth, divided by the divided by the apparent depth. Now you can work this thing. This formula was worked out due to some trigonometric basic trig ratios. Okay, so let's see, how do we get the apparent? Oh, I spelled wrong here. Oof. Apparent. Yep, there we go. So, and that n is equal to 1,33. So, if you want the apparent depth, if you were to stand here at the pool, what depth do you see? The pool is actually 1 meter, but how deep do you see the pool? Okay, so we know that the apparent depth, let me stop right and start writing in my original blackboard color. So the apparent depth of the pool, the apparent depth is equal to the real depth divided by the refractive index. Okay, so this is how you get the apparent depth of a pool. You take the real depth, which is 1 meter, and you divide it by the refractive index of that water, 1,33, and you will see the answer is 0.752 meters, which is approximately 75 centimeters, 75.2 centimeters. So the depth that you see while you're standing at the edge of the pool, you see 0.75 or 75 centimeters. You see that the pool is 75 centimeters deep. But the actual depth of this pool is 1 meter. Okay? So note that before you dive into the deep end, if you are seeing, uh, in this case, if you are seeing the pool as 2 meters deep, do not dive in because it's most likely 3 meters because you are seeing the apparent depth of the pool. That's why when you look at the water, oh, it's not that deep. Then you dive in. Now you are struggling for air because you're sinking like a stone. Okay, because you misjudged. You did not misjudge the distance. You saw a depth that is less than the actual depth. Okay, and you can check if you have a pool that has a deep. Let's say we have some of these deep pools at 5 meter distance. Let's see what happens if it's 5 meters. What would you see if the pool has an actual depth of 5 meters? Okay, water does not change there. So let's see if it's 5 meters. 5 divided by 1.3. I'm just getting my calculator here. It's on in my hand here. 5 divided by 1.33. If the pool is actually 5 meters deep, you will see the pool as 3.75 meters. Okay? You are seeing that the pool, now it's 3.75, I can swim there. But in actuality, that pool is 5 meters deep. The distance that you see, the apparent depth you see, and the actual distance is different. Okay? So note that before you jump into the pool, take out your phone and then calculate what the real depth is. You can do that, or you can just, get a stick and measure it, or just read what the actual depth is. It's usually in the pool. Okay, but if you want to show off to your friends at the pool, you can show them that you can calculate the actual depth and the apparent depth you see. Now, next question. These things will come in handy. It's summer, okay, but nobody goes to the summer to measure. Abiwe, you have a question? Go ahead. Don't worry.
Okay, thank you, sir. So sir, according to the two examples you've just given us,
Yes.
would I be correct if I said if the second medium's n is greater than the first medium's n,
Yes.
then whatever object we're seeing is quite smaller or further less than what it appears to be?
Yes, you will see the apparent depth you see will always be less. Okay. But here's the thing now, if you reverse your question now, that's a good question by the way, River. If you reverse the situation, if you are standing in, say, something that has an apparent, it's not going to be a lot, there's not a lot of examples, but if you are standing in something or you're about to dive in something that has a refractive index that is less, okay, let's say you are in glass and you're about to dive in water, okay, then the apparent depth that you see will
I think
be
it's gonna be quite larger.
larger than what it actually is. Yes,
Yeah,
just the
because
reverse. Because you're
I'm
going to
also wearing
divide by
glasses.
something less than 1. So you're going to divide by zero point 0.9 or something. You get that? The reason
Yes,
why
sir.
it's less is because when you divide by 1 comma something something. So it will always be point something. So it will always be a fraction of the original length. But if it's reversed, you're going to divide by point something, which means the apparent depth that you see will be larger. Okay. So in that case, do not dive because the apparent depth will look like it's 2 meters, but when you dive, it's just 1 meter. You break your neck. Okay.
I see, sir. Thank you.
Okay. Cool. Okay. Question number 3 for the ladies. Bottles of perfume sometimes have a thick glass. Okay. Also for the gentlemen, cologne. if you're using cologne, uh, you have they sometimes have a thick glass, and the refractive index of this glass is equal to 1.5. Okay, for glass. And you have a thick glass wall, which gives the impression that the volume is larger than it is. So please note, ladies, gentlemen, the same thing goes for what my wife likes this, Q-Tex, nail polish. Okay, the reason why they make that thing so thick, the glass, and then when you pour out or you spray the cologne or perfume or your nail polish, it is much less than what it looks like in the store. It's because they make that glass so thick, that glass wall is so thick. It's because of that reason. So it looks, the volume looks so much, and then when you spray it 3 times, the perfume is done. Okay. Now, bottles of perfume or nail polish have thick glass walls which have a refractive index of 1.5, which give the impression that the volume is larger. That's why they make it thick. They want you to think that the volume is actually larger than it is. Now assume a cylindrical bottle. Okay, it has an inner radius of 1 centimeter and an outer radius of 2 centimeters. How thick in centimeters would the wall appear if you could see a mark on the inside surface? Okay, let's say this is what is happening. Uh, if you have this bottle, okay, this is the perfume, that's the outer, but inside, this is just the glass. This is the glass. This is the glass here. This is the actual perfume in here. Okay, this is what's happening. This is Chanel, whatever, Whisper. My wife likes Whisper. Uh, whatever perfume you choose to be in there. You smell like, I saw Justin Bieber's scent or something the other day, or you smell like Usher, or smell like any famous person. Okay, you smell like Cristiano Ronaldo. So this is a perfume bottle. It has a thickness, the inside radius. Now picture this as a round. I just drew it like that so you can see. Now it's supposed to be a round. Okay. Now it has an inner radius of 1 centimeter and an outer radius, meaning if you were to look at it from the top, the inner radius would be 1 centimeter, while the outer radius would be 2 centimeters. Okay, and the perfume is inside this inner radius. Okay, now let's say they make a mark on the inside here. They make a mark. How big? You can see a mark. How thick in centimeters would the wall appear? How thick would the wall appear? You know that this wall actually has a thickness of 1 centimeter, right? Because you can actually calculate it. It has an inside radius of 1 and an outside radius of 2, so it should have a thickness of 1 centimeter. Okay. Now let's calculate if how thick does this wall actually appear? How thick does it actually appear? Now, this is the formula. You can write it down. The actual thickness is equal to outer thickness minus the inner thickness, right? This is what it actually is. Okay, that's 2 centimeters minus 1 centimeter. So the wall is actually 1 centimeter thick. This is what the wall actually is of this perfume bottle or the nail polish. Okay. Now let's use that depth formula that we had earlier. Okay, which says the apparent thickness. Okay. Now this formula, that one I had earlier was for if you were to look at a pool or something. Now I did not write the complete formula earlier on. Okay, I did not write the complete formula. This is the complete formula. It says the apparent depth divided, and I'm going to show you now why I did not write. I actually did write it. You just okay. I'm going to show now. The apparent depth. By the way, I write terrible. It's like a crab that is high. Okay, so the apparent depth divided by the actual depth should be the ratio of the refractive index of air over the refractive index of glass. Okay. Now earlier on, I did not write this as a ratio. Okay. The reason being, for earlier on, it would have been the other way around. It would be the actual, remember, real was on top. Remember, it doesn't matter which way you write it. It's a ratio. Okay. Remember earlier on, I wrote a formula like this. Let me write it there as real. I'm going to write it this way. It was real, remember, over apparent. Real distance over the apparent distance. And that was equal to the refractive index of the water. Okay, but it should, in actuality, it was the refractive index of water over the refractive index of air. The reason why we normally don't write that of air is because it's 1. You guys get that? Show of hands. This is what the actual formula should have looked like earlier on. But I did not write this part because the refractive index of air is usually taken as 1. So we usually never write it if we're dealing with air. Does that make sense? Just a show of hands if you understand that part. This is the actual formula, but earlier on I just wrote it as NW, or I did not write the W, I just wrote N. D real over D apparent. I wrote it like this earlier on because normally it's just a convention. We just assume if we are dealing with air, we just write, because air's refractive index is 1, we just write the refractive index of whatever we're dealing with. But in this case, we are not dealing with air, so we need to write the refractive index as a ratio as well. So it will be the refractive index of uh, glass, in this case, over the refractive index of air. We're still dealing with air, but now I'm writing it actually. And it will be the real distance divided by the apparent depth or apparent distance. Okay, now I wrote it in full this time. So now the refractive index of glass we've been given as 1.55. That of air is 1. That's why we normally don't write it, because it's going to be the same thing. And the real distance is, in actual fact, the real distance we calculated to be 1 centimeter. Remember, we calculated the thickness of that glass to be 1 centimeter. What is the apparent thickness? What, when you look at this perfume, how thick does that glass appear to be? Okay, just write apparent. How thick does the glass appear to be? This is 1.55. This is just 1. Let's calculate it out. The apparent distance, therefore, if you do this, is equal to 1 divided by 1.55. Now 1 divided by 1.55, of course, and then multiply, well, that is 1.5. 1.5 divided by 1 is 1. You divide on this side, you multiply by that side. It's just simple math. And you get an answer of 0.67 centimeters. Okay, so the glass, ladies and gentlemen, appears to be 0.67 centimeters thick. Okay, this thing is actually 1 full centimeter thick, but to you it appears almost half a centimeter thick. Okay, it's 0.67 centimeters thick. So it appears that there is a lot more volume. It appears much thinner than it actually is. Okay, does that make sense to anyone? Show of hands if you understand this question. The glass or the perfume bottle or the nail polish appears to be, the glass appears to be much thinner, and it looks like there is a lot of perfume or whatever in this bottle, but then it actually is. Mr. Speaker, you can go. Go ahead. If you want to type, go ahead. If you want to speak, cool. I see your hand is raised. Okay, Aviva, cool. Go ahead.
So would I be wrong if I say if I didn't understand the question?
Mm-hmm.
Would I be wrong if I considered the fact that the perfume would actually be occupying a less space than the actual um object the actual container it's being carried by? Because if you look at the radius in the outer part and the radius in the inner part, the
Mm-hmm.
radius in the outer part is greater than the radius in the inner part.
Yes.
So if I consider talking about the shape in the exam or in a test, would I be wrong?
It depends. You see, in this case, I understand more or less since you're explaining it to me. I know where you're going with this. You're just going to calculate the volumes, and then you're going to explain from volumes on why it would appear like that. But it depends on your lecturer. Some lecturers mark strictly according to memos. I don't usually do that. I mark strictly, but I'm lenient. But if you are doing FVV, Dr. Manar remarks decently. Or if you're doing PHYV, it's Dr. Ugesa, right?
So Mr. Minar does not do
Oh
optics.
yeah, Dr. Khashek. Is it? Huh?
Yes, yes.
Okay. She's reasonable. Okay, but it also, since they're big classes, there are also other markers involved. Okay, so I
Okay.
don't know. But rather do it the way that you've been taught in class or here, and that would help you much better.
Okay, thank you, sir.
Okay, now Mr. Zipika asked, what if there was an object floating inside the perfume? How would we calculate that? What would we have to include air, water, and glass? That's an interesting question. The answer is yes. If you wanted to calculate, say, let's say, I understand what you're saying. Let's say this is a perfume bottle. Okay. Now you have the inside of the perfume bottle. But inside the perfume bottle, you have the actual perfume. And in there, there is a, let's say they put nice things in here, a rose. Okay. They put a rose in there. And they ask you maybe, how high is this rose from the floor? Okay. How high is the rose? In actuality, the rose is, say, in the middle. And they ask you, how high do you think this rose is? Then, yes, Mr. Speaker, then yes, you will need to take into account the the refractive index of the perfume itself as well. Does that make sense? Just a show of hand. Does that make sense? Okay, Mr. Viewer, go ahead.
I'm sorry, sir. Um, is the refractive index of the perfume equal to the refractive index of water?
No,
So they're not the same.
no. I know he said there air, water, and glass. It depends on what is in here. Every substance has its own refractive index. But remember, it must
Okay.
be optical. It must be something that light can pass through. Like for
Mm-hmm.
instance, uh, this pen will not have a refractive index because it's black. Light cannot pass through it.
Yeah.
Okay, or where this my shoe is, unless I've seen some weird shoes. Unless you have shoes that are see-through, light cannot pass through it. But why would you wear
Okay.
see-through shoes?
I don't
See,
know, sir.
see your toes all crumpled up inside the shoe. Anyway, let's go ahead and go to our next question. This question is the one with the aliens. The inhabitants of a planet in another galaxy have their eyes at the exact center of their 4-meter long bodies. Okay. So this is this being from another body, from another planet. Their eyes are right here, and they are 4 meters long. Okay, so they have an actual length of 4 meters, and their eyes are exactly in the middle of their 4 meters. So at 2 meters, their eyes are located. How long must a plane mirror be for such a creature to be able to see all of its body in the mirror? So how long must a mirror be so that it can see its entire body in this mirror? Okay, let's work it out. Okay, the creature's total height is 4 meters. Okay, the creature's total height is equal to 4 meters. Okay. Now the minimum length of the mirror needed to see the entire body is half of this. Okay, the minimum length that you need to see the entire body, since its eyes is located halfway, is half of this. So, and the reasoning is as follows. Okay, uh, go ahead, Aviwa.
Okay, so wouldn't we have to make the mirror like halfway taller than the body is? That means it could be like 2 meters long.
Yes, that's the correct answer, by the way.
Okay, thank you, sir.
Okay, so in this case, for this alien to see the top of its body, a ray of light, right? For this alien, let's draw the alien. It's a square alien. Best way to explain this. For this alien to see the top of its body, okay, a ray of light must reflect from the top of the mirror and travel to the creature's eye. So let's say here's the mirror. Here's the mirror. This is the mirror. So there's the mirror. Now a ray of light must travel from, to see the top of its body, it must travel from, uh, it must reflect from the top of the mirror and travel to the creature's eyes. Okay, so it must go there, bounce off, and then travel to the creature's eyes. Okay, so it must bounce off and travel to the creature's eyes. Now the distance from there to there is 2 meters. Okay, now you guys remember the law of reflection? It is very simple, the law of reflection. It says that the angle of incidence must be equal to the angle of reflection. Okay, if the eyes are there, okay, there's the eyes in the middle, there's the top of this creature's head. Okay, now if the ray is to bounce off the mirror and go back, the angle there must be equal to that angle. Okay, now this length is 2 meters because the creature's total length is 4 meters and its eyes is dead in the center, dead set in the center. Okay, therefore, if this angle is equal to that angle, it means that this distance must be 1 and that distance must also be 1. Same reasoning applies to the bottom. Okay, that's just how I reason this out. Okay, same reasoning applies. Okay, that means the distance there is 1 meter up to there, from the middle to there is 1 meter there. So you must divide this creature into 4 equal parts. Okay, so the closest point that this mirror must have a reflection at must be here. The minimum size of this mirror must be from there to there. Does that make sense? And that distance from there to there is 1 meter, 2 meters. So that distance must be 2 meters. So the minimum mirror distance must be 2 meters. Does that make sense to everyone? You cannot have the mirror smaller than that. Otherwise, it will not see the top of its own head. Okay. Anyone else confused a bit? If you are, just raise your hand and I'll try to explain it better. If I can. No one, so I'll continue. So this mirror needs to be at least 2 meters tall for this creature to see its own head. Okay, let me see. There we go. By the way, the distance also plays a role. Okay, because they don't specifically say that, but And I know my wife does this. If she wants to see her figure better, she moves away and then she twirls and whatever. But the closer you are to the mirror, the less of your own body you see. Okay? The further away you are, the more of your body you see. Okay? Okay. I think this is the almost done now. Almost there. Now, the object in a ray diagram is perpendicular to the principal axis, but does not have one end lying on its principal axis. The minimum number of rays that must be drawn in this ray diagram in order to determine the position of the image is. Now, you can go and read about this. It's just a theory question. You just ask how many rays, light rays, do we need to determine the position of an object. And it you will see in your books, it is just three. Okay? For any object, three light rays is enough to determine its exact position. Question number 36. In a very cool question. If you stand closer to a concave mirror, by the way, this is convex, this is concave. Okay? So here we have a concave mirror. It's not a lens, it's a mirror. So if you stand closer to a concave mirror, okay, closer to than a distance of one focal length, the image you see, okay, let's say this is a concave mirror. All the light will be reflected. Let's say you have incoming light rays, incoming light rays. These light rays, concave mirrors, what they do is they reflect the light
Yeah,
to a
so it's
single point. So they will do this. All the light rays will be reflected to a single point. I hope you understand that. So basically there. Now, if you are standing closer to a concave mirror than one focal length, then remember focal length is where you will see your exact height. Now, if you were to stand closer than a focal length, okay, the image that you will see is virtual. Okay, the image that you will see is virtual because according to your eyes, if you look in this mirror, you will see yourself like this.
small.
Uh, you will see yourself much bigger. Let's say this is
Not
you.
small.
Now bigger. I'm going to show you now why. I understand why you just asked that. Let's say I'm going to draw four lines, right? Just four lines, so you can see this. What you're going to see is the lines are going to start crossing. Now this is a huge over exaggeration. So this is what you see. Now let's say this lines comes from you. Here you are. These lines come from you, straight from you, like that. These lines come from you. Now in your mind is going to trick you. This image is going to look like the light rays comes from there. Remember now, you are going to see a small a person here. I understand why you just said smaller. The person here is going to be smaller that is created. But to your eyes, this person is going to look humongous. Because remember, according to what you see, it looks like the head is here. Remember, the light ray comes from the head. So it looks like the head is there and the feet is there and the arms are there. Does that make sense? It looks like the light rays are coming from outside, from behind the mirror. That's what it looks like. It's not actually behind the mirror. The person is not there. You're actually standing there. But it looks like the light rays are coming from behind the mirror. Okay? Because of this, the light rays being bent. Okay. So what you see is a virtual image. It is virtual and it is upright and it is magnified. Okay. It is virtual. It is upright and it is magnified. Okay. So let's see. Virtual and it's upright. D. Let's check. Indeed, it is correct. Last question. Okay, this is where you need to understand what is a concave mirror, a convex mirror, a convergent lens, and a divergent lens. Okay, now of the possible statements that parallel rays are brought to focus. Now, how do you focus parallel rays? There are two ways you can do it. First of all, we just did one. You can focus parallel rays by using a concave mirror. You can focus these rays by using a concave mirror. This is a concave mirror. You can focus the lens by using a concave mirror and a converging lens. A converging lens. You can also use a converging lens. Okay. Now a lens would be uh, too big. Let me draw it like this. Smaller. Ugh, a terrible lens, but it should look like that. A converging lens. It will cause it to diverge here on this side due to diffraction and that. But when you're looking, it's not a double-sided. That's the problem. I drew it double-sided. Converging lens. The light rays will go through. Okay, so a converging lens and a concave mirror will both converge parallel rays. Okay, so a concave, what is it? Concave or concave mirror, number one, and a converging lens, number two. So no, number three. So one and three, and let's check, and that's correct. Okay, ladies and gentlemen, that is all that we have time for today. I did take longer than expected. I hope you understand what we did, and thank you for listening. All the best for your exams and tests, and have a nice rest of your week. Okay, bye bye. Thank you, guys.